I'm a bit worried that the level of the presentation isn't going to be really what people are. Obviously, people are expecting something a little bit.
Very fast and a bit every third word.
So, I was thinking going pretty slowly actually, because compared with some of the other speakers, I looked at their slides and I've got a rather modest amount of material. So algorithms and complexity. So first of all, I should apologise. I mean, it's very bad manners to sort of just ignore the workshop, just come in, give your talk, and then go again. But because of teaching this week, I can't come to the rest of the workshop. I'd very much like to. So there aren't slides either. So how to catch up with anything that I cover? Almost all of it will be. So I gave a grad course at ETH, and you can spend money on the lecture notes buying them from Berkhäuser. They're very competitively priced. Or you can cheat by going to my webpage. And so if you go to my webpage and then go through the link to publications, there's some lecture notes, ETH lecture notes. And chapters 1 and 2 will cover most of it, but in the second talk I'll be talking about things. So that was 2000, supposed to be, 2000, and then I'll be touching on something post-2000, so at that point I'll give you another reference. But this covers. So this is basically Algorithms and Complexity 101, so there are going to be some people in the audience pretty insulted by it. It sounds like an impossible task, right, to do anything in a couple of hours, but given the scope of this workshop, people are going to be interested in counting problems, I imagine, evaluation of partition functions, and so this is a kind of subdomain of algorithms and complexity. In fact, if you pick up an algorithms or complexity book, 90% of it plus is going to be about other topics. It'll be about decision problems coming from logic. Does a graph have a Hamilton cycle? It'll be about optimization problems. Given these cities and these distances, what's the minimum traveling salesman tool around them? So that's the biggest part of algorithms and complexity. But if we restrict our attention just to counting problems, so I'm going to be counting combinatorial structures, but also weighted structures. So I'm going to incorporate partition functions, say the Ising model, where you're counting configurations but with weights. And even I'm not going to get to this, but even I would include infinite sums. I would include volumes within this, but I don't think I'll be talking about that here. Then the whole thing becomes actually quite feasible. And the strange feature of this part of the world, because algorithms, there's lots of clever techniques. In complexity, there are lots of nice arguments going on. But in this counting world, unfortunately, there aren't very many techniques. The ones that exist are powerful and interesting, but they're few in number. And in fact, so lecture 1 is about algorithms. So this is the positive view of the world. In fact, there are basically 2 killer techniques which cover almost everything that you need to know. So, so the first technique applies to exact counting. So you have a counting problem and you want to know the answer exactly. And there's a certain technique which recurs. And you've seen actually, I think, already one example of it, but I'll give another. So there's been some interplay between the speakers this week. And then I'll go on to talk about when exact solutions can't be got, we'd at least like to get approximations with good relative error. And again, there's kind of one killer technique there, which I'll kind of explain by an example. So what I want to do in the first lecture is, so there's the sort of problems we want to tackle, I think, in the context of this meeting are sort of counting, and some of these structures I mean, all of these structures I was imagining you'd get in Bill Jackson's course, but he managed to miss out matchings, which is going to be my main thing. And of course, this is multidisciplinary, so you'll need a dictionary to translate between the different groups. So, for example, and all of these I can consider in a strict combinatorial sense or in a weighted sense, independent sets in a graph. So actually I'll restrict attention to graph problems. So independent sets, you've probably seen that one. So those are, you have a graph, so always the instance will be a graph, and you're looking for a subset of the vertices such that no pair of vertices are adjacent. So in the physics world, this is the hardcore gas model. So usually in this dictionary, there's a fairly precise translation between the terms. And what thing I want to concentrate on, so I'll even define what these structures are, is matchings. So both perfect matchings, which in the physics world is these are dimer covers. So that's my. Is this?
What's funny?
No.
It's funny to see the buzzwords and the mathematics.
Yeah. Okay. Well.
So physicist is not a buzzword; it's just an ordinary.
So anyway, yeah. So there's
Then
unintentional.
language and you don't understand anything what they are saying.
So, and then matchings of all sizes, and this is monomer dimer. Okay, so these are so matchings. Since Bill didn't get to it, these are sort of the dual concept to independent sets. So these are subsets of the edge set which are pairwise disjoint. They don't have any vertices in common.
I did line graphs.
Yeah,
So you could say
it's the
that
same
there
as
were
independent sets in a line graph. Very good. So for any counting problem, of course, there is an algorithm which is to exhaustive enumeration. You could go through all the possibilities. So you could go through all the subsets of the vertex set of a graph, and for each of them decide whether it was independent, and then increment a counter. So what the game is to find more efficient ways of going about it. So that's an exponential time algorithm where the running time will scale as an exponential in the size of the graph. So the problem with the algorithmic problem is to find ways of shortcuts to enumerating things which avoid this exponential growth. So we'll be looking particularly for algorithms which scale polynomially with the size of the graph. Say the number of vertices. Call n, in computer science, n is always the instance size. And so I'm looking for a running time which is n squared or n cubed or something like that. So let's have a concrete example of a problem where there is a shortcut, where we don't have to go through all of the exponentially many structures. And this is a classical result, very nice, going back to the early 60s. Right, so, and it's for counting perfect matchings in planar graphs. So, just to give it a sort of a spurious physics dimension, I will make my graph look like a fragment of Z2. And the things I'm interested in, oh, that's not very good. counting are perfect matchings. So that's a matching that has to cover all of the vertices of the graph. So an example of one of these things is structures is like this. So if there are 2n vertices, there should be n edges in the matching. So that's a typical example. So 2n vertices, n edges, each of them occupy 2 distinct vertices, and so those are the dimers that have been packed in to the lattice. Now, the lattice structure is unimportant for what I'm going to say, but the planarity of this graph is significant. So the reference for this is, so that's my original, okay. So in the notes I referred to Castellane, 63, and certainly everything is in there, but actually I should also have mentioned Fisher and Temperley, because already in 61 most of it's in there. I think it's a somewhat restricted to the case of lattice graphs, whereas in Castellane it's more clear that the thing is applicable to planar graphs in general. But a lot of the ideas are already in this earlier thing. So I don't know how they thought about it, but the key step is the leap is to try, instead of trying to count the perfect matchings as such, you count pairs of perfect matchings. Which so that's the fun bit of it. So we're going to so if we start, let's continue with this graph as a and we'll do the algorithm by example, as it were. So that's my graph G. So first step, and this is where the planarity comes in, essentially, is to orient the edges. But you have to do it in a certain way, and I'll explain. So I will do it and explain what the key property of it is. So let me do it. It's not unique by any means, but it's enough in Z2 to orient everything upwards here, and then to alternate right and left on the horizontals. And the key property of this orientation, so this is G with an arrow above it, the oriented version of G. The only key thing is that if I look at any face in here, and I go round clockwise, then there's always an there's always an odd number of edges which are oriented in the direction that I'm going. So so yes, no, yes, yes. No, 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 yes. So that's the key thing there. Right, so that's well, of course, if the graph wasn't planar, it's not clear what I'd be. You know, I talked about faces there, but it's not clear what I would mean. So okay, so and the next thing I want to do is now go to in the next step go to a graph. Let's call it a sort of double arrow, in which I replace, so the operation I'm using to get from this oriented graph to the doubly oriented one is to replace each edge here by a pair of anti-parallel edges, where I'll give the edge that's oriented the same direction as the one in G. That'll be the +1, and then I'll have a -1. So the adjacency matrix of this new graph will be skew symmetric. I don't think I'll draw the whole thing, but I'll just draw the top corner of it. It will look something like that. So now we've got pairs of anti-parallel edges, and this will be +1, this will be 1. And this one goes up, so that will be the +1. That will be the -1, and this one goes this way, so that's the +1. That's the -1. And this one goes up, so that's a plus, and that's a minus. And the graph continues up here. Right, so the first, so this is going to be sort of a slightly hand-wavy thing. Let's take, as I say, what we're going to do is to count pairs. So count, this is the key to it, count pairs of perfect matches in G. And then obviously at the end of the day we just take the square root. So. Right, so let's take this, this red one, and I need another colour, so blue one. So red one will be as before, and the blue one might look like this. I mean, sometimes the blue and the red edge might coincide. No reason why that shouldn't happen. And when you do that, where obviously a perfect matching has the property that the degree at every vertex is 1. So if you superimpose 2, you're getting a graph, a subgraph, in which each vertex degree is 2. So it's going to be a bunch of cycles, right? Of even length, because it's composed of equal numbers of red and blue, and the cycle might have length too. It might be one of these degenerate things, that's for sure. So what does that structure look like over when you look at it over in here? Well, you can view this as a so-called cycle cover. So a cycle is a path that returns to its starting point, and a cover because it hits all of the vertices. So over in G double arrow, I can interpret that pair as being a certain cycle, which maybe I should have done in colour. Something like that. So. And indeed, it's actually 1-1, this correspondence between pairs of perfect matchings here and cycle covers over here. And that may not be clear at first, but you see, in the case of this trivial, when the edges lie above one another, there's only one pattern here, and similarly, there's only one cycle here. But in any of the other cases over here, I've got two choices. I've got blue, red, but I've also got red, blue. But equally, because this is, I've got anti-parallel edges here, I've got a clockwise cycle and an anti-clockwise cycle. So if there are k cycles, there are 2 to the k different orientations of those guys, but equally, over here, there are 2 to the k ways of colouring those red and blue. So
it's not a canonical bijection. You need some convention.
Yeah, you could say either there's a convention, or maybe you're not interested in the bijection at all. Maybe you're just interested in the number of these things. In which case, yeah. Okay, so we're done. If we could count the number of cycle covers, even cycle covers in G. Now, it turned out perhaps this is a bad example because this is a bipartite graph, so all of its cycles are even. Maybe a better example would have had some odd cycles, so that we would have to exclude them over here. But of course, this is just a planar graph, so if it had a triangle in it, you're quite at liberty to draw a triangle, a cycle of length 3 here, and that shouldn't come into the enumeration because it doesn't correspond to a pair of perfect matching. So that's where we are at the moment, right? We've got a we've reduced to counting even, let me call them even cycle covers. in this thing here. Where at the moment I'm ignoring the signs. Right. Now, cycle covers, they correspond very closely to the determinant of the adjacency matrix. So let me call this is the skew adjacency matrix of the oriented version of G equals Aij. This will just be this is just the adjacency matrix of this graph here. So whenever you've got an edge from I to j, there will be a +1 entry at ij and a -1 entry at ji. Okay, so it's because the anti-parallel edges have opposite signs. So, what we do is we look at the determinant of this and, well, just see what happens. And magically, I mean, there's a whole lot of signs around the place, but magically they all work the way we need them to work. So let's have a look at this thing. Well, it's a sum over sigma permutations of the vertices of the sign of that permutation. And then there's a product over I, or I equals 1 to n of ai sigma I, where this is the adjacency matrix of the skew symmetric adjacency matrix. And you see, of course, each of these, this is a permutation, so it breaks down into cycles, and each of those.
Sigma I or sigma j?
I've got a product over I. These are supposed to be, yeah.
N is the number of vertices?
N is the number of vertices, yeah. Yeah. Yeah, so yeah. So that's supposed to be the expression of the determinant of this matrix. Okay. Now this, so these permutations, think of them as decomposing into cycles. They will be, you can interpret those as cycles in the graph, as above. Now, what happens to the odd cycles in this expansion? So now let's have a look at this expansion. I don't want the odd cycles, unfortunately. Of course, this is not. You're not going to get in an hour. You're not going. You're not going to get 2 proper proofs in an hour. But I just want to get to the stage where you're well inclined towards believing that this is okay. Okay, so think about, because this is an anti-symmetric graph, whenever I have, I've got some permutation that includes, so this is supposed to be not the entire permutation, but this is some permutation that includes a cycle of length 3, for example, on the vertices A, B, and C, then I can match that up, and I could have some canonical rule, choose the smallest cycle in some ordering. I could match that up. I could choose the smallest odd cycle in some order, and then I could flip it. I could reverse it. If it's a clockwise, I could go to an anti-clockwise. And in this way, I can pair up all of the cycles which contain some odd cycle. And the nice thing is that the sign switches between these two, because if this had been say a +1, +1, -1, then this would be a -1, -1, +1. So if this one contributes -1 to the sum, then this will contribute a +1. And of course, this bit of the expansion has remained the same. The sign is unchanged because I just replaced one 3 cycle by another 3 cycles. So Yeah, so the parity of the permutation is unchanged. So any permutation sigma to which contain odd cycles will just cancel out in pairs in this sum. So I can restrict the sum to just even cycles. But things can still go wrong because, of course, I want each even cycle cover to be counted once, plus 1. And I've got some trouble here. I've got a -1 coming possibly from the permutation, and I've certainly got loads of -1s in here. So I'm going to have to get pretty lucky if those are going to cancel out. But we do get very lucky. That's the whole point of this business. And the reason we get lucky is the following. If we look at, again, at some permutation, and let me concentrate on a cycle within it of length 4, then and this is where we need the very special properties of this orientation, that every even cycle has an odd number of co-oriented edges. That's where we need this property. If I look at this cycle within the graph G double arrow, I'm bound to have an odd number of -1s in it. There'll be an odd number of counter-oriented edges. So I might get -1 here, -1 here, -1 here, and a +1. So in this part of every even cycle will contribute -1 to this part, but just by the way I managed to orient the original graph. But equally, this is a product of 3 transpositions. So its sign is -1, and so we get a contribution -1 also to the sign here, and that cancels out. So this permutation is composed only of even cycles, and each even cycle contributes a -1 here and a -1 here, +1 overall. So magically, I mean, this is the beauty of the method, that somehow the signs, which normally work against you, I mean, the reason the determinant isn't all powerful in combinatorial enumeration is you've got these pesky signs, but here it works to your advantage because it kills exactly the signs that you need to kill. So what you need, for this to work, you need to be able to orient the graph in a certain way. So it's called. So what you need is a Pfaffian orientation. So we need Pfaffian orientation of G. And I'm not sure how I can say in words what it means. It means that whenever you have a cycle cover, whenever you have an even cycle cover in the graph, in the undirected version of the graph, whenever you have an even cycle cover in the graph, then in every cycle there'll be an odd number of counter-oriented edges. So in fact, it's exactly what you need to get this to work, right? So, and it turns out this is not the same thing as planar. So, but any planar graph. So there's a simple inductive. Well, there's not too difficult inductive argument on number of faces, which tells you that every planar graph does have a Pfaffian orientation. But there are non-planar graphs which are also Pfaffian orientable. There's a long-standing complexity question here of whether there's an efficient algorithm to determine whether a graph has a Pfaffian orientation, which has been solved by very high-powered methods in the case of bipartite graphs. And is it still open, Bill?
Well, it kind of worms for non-bipartite graphs.
For non-bipartite, it's still open. So the question of whether one of these exists is open in general. But for bipartite, it's solved by very powerful techniques.
Can you maybe just formulate the answer you're claiming? Are you saying this is on the nose equal to the number of?
So this determinant will be equal to the number of even cycle covers in G this. So if I take the square root of it, I will have exactly the number. So this is an exact algorithm, exactly the number of perfect matching. So I'll try and normalize my terminology to be graph theoretic for this.
You need
For this
to
hour.
know one little piece that there is a cubic time algorithm for the determinant.
Yes, okay, we're coming to that. Yes. So why are we in? Yeah, sorry.
Sorry, so if a graph is not planar, what is the definition exactly of having a Pfaffian orientation? Is it every...
Well, it's still that what I said still makes sense, right?
every even
It's saying I'm saying if I have even if I have any if I have any even cycle cover, so I don't need planarity for that. If I look at any cycle within it, there'll be an odd number of edges co-oriented. So I don't need, but Bill's eager to say, it adds some.
Maybe one definition for a Pfaffian non-bipartite graph would be you look, so here, for planar graphs, you can just consider the faces. So we just consider special cycles. We say a cycle is central if when you delete the vertices of the cycle, there remains a perfect matching.
This is equivalent to what I said, yeah. I don't know whether it's easier or not. But.
So an orientation is Pfaffian if each central cycle has an odd number of edges directed in each direction. So all cycles are even, so if there's an odd number in one direction, there will be an odd number in the other direction as well.
Yeah, so it doesn't apply to all cycles. So for example, getting into, I think I'm right in saying if I took that cycle there of length 8, it doesn't have the property, right? It's 1, 2, 3, 4, which is even. But it doesn't fit Bill's description because after you've taken that cycle out, you've only got one vertex there, so you can't. So the way I said it, you can't complete that to a cycle cover. The way Bill said it, you can't find a perfect matching on the remainder of the graph. But since you could always take 2 copies of the same perfect matching and put them atop each other, it's the same. It's the same statement.
If you take an example, take points which are like in the picture, like in an array, and connect everybody in the same column and everybody in the same line. Is this does this have a Pfaffian orientation?
No, it's got huge.
It's incomplete bipartite graph.
So in each, it's not complete. I mean, in each row and in each column, you have a complete graph.
Cartesian product.
Yeah, that's got huge
So it's not
pleats in it.
bipartite.
Yeah.
Yeah, it's not.
So it's certainly not. It's got massive pleats, so it's not Pfaffian. So, yeah. So anyway, we have to come to the punchline. Why is this any good from an algorithmic perspective? It's that the determinant is nice and easy to evaluate. If you look at that, it looks exponential, right? Because I'm having to sum over an exponential number of permutations. But we all know that we can evaluate the determinant by Gaussian elimination in n cubed time, where n is again the number of vertices. So this is exactly what I'm looking for. It's a program whose running time scales as a polynomial in the input size rather than as an exponential. So it comes within the
What is the
whole. Thank you.
complexity of finding the orientation?
And the complexity of finding the orientation. If it's planar, it's actually, well, I said there was a simple inductive proof for planar graphs. It's constructive. So you could run the induction backwards and it would give you an orientation. So you would orient the smaller graph and then add a bit on. For general bipartite, it'll be polynomial. It's Seymour-Robertson stuff. So it's not good. Seymour-Robertson, yeah, okay, so it's that technology. The author list is Seymour-Robertson, Thomas, right? Yeah?
I think they decompose, so the theorem says that if there is a bipartite graph has a Pfaffian orientation, if and only if the bipartite graph can be decomposed into planar graphs and the Harewood graph, special bipartite graph. And they're joined along small cuts in some sense. So I think if you have the planar algorithm, you could use it for this more general family by handling the small cuts.
Okay. But for planar, for lattices, all your favorite lattices, of course, you can do it by hand. There's always a regular pattern that does the
What's
job.
important though is that this is also a polynomial time algorithm, right, of assigning plus minus ones.
Yeah.
So what is
Yeah.
what is the result of that applies to bipartite graphs? Like you said,
there's a
So there's
polynomial.
a characterization of bipartite graphs which have a Pfaffian orientation.
Okay, so it's a polynomial time characterization of those bipartite graphs that have that. Okay.
It's a characterization that leads to a polynomial time algorithm to find a decomposition into bits which are essentially planar.
Oh.
And once you've got the bits which are essentially planar, you can run the algorithm for planar graphs.
Okay.
So graph theorists are obviously numerous in the audience. While that's going on, I thought I'd just construct a list of things that are handled by linear algebra, by reduction to determinants. So perfect matchings in planar graphs, we've just seen. Spanning trees in arbitrary graphs, you've seen, I think. Is that right? Yep. Dave Wagner did that. See, so I'm keeping track of this. And then the ferromagnetic easing model. But only if it's planar and zero external field. So we don't have time to stop and say what that means. So it'll either mean something to you or not. But okay, so the mysterious thing is that all of these, the game is to construct a certain determinant by Gaussian elimination, figure it out, and that gives you the answer to the problem after taking a square root or something straightforward. And so you've got another one to add to this.
Just 10 seconds of publicity for my own talk tomorrow. So the perfect matching, you are going to see that it is central charge 1. That will be evident tomorrow. Spanning trees is c equals -2, and the easing model is c equals 1/2. The first of the things will be evident tomorrow.
Well, I'm going to be Newt tomorrow. So this is just a tiny little vision of the. Okay, good. So maybe this is so Les Valiant will be meeting. No, I mean in some kind of figurative sense this afternoon. Was intrigued by this fact that exactly the known cases where almost all the known examples where you could count things exactly work by reduction to determinant, and try to give some complexity theoretic explanation of this, which was only, well, it was sort of, was interesting in its way, but certainly not. It doesn't really give an explanation of why this seems to be the only technique. So at the moment, we leave it as a mysterious fact. So as far as exact enumeration goes, the message from this is that basically there's one golf club and it's Gaussian elimination. But you need some, this is it's a nice construction. So you need some ingenuity in order to see how to construct the matrix and then to see why it counts the things that it's meant to count. So you need to figure out some way of using the signs in a constructive way. Now, I was expecting to be at this point a bit earlier on, but I guess people are expecting that. I wasn't expecting the graph theoretic. So very quickly, I will discuss the other golf club, which cuts in when you're looking for solutions within good relative error. So what is the game now? It's motivated by the fact that there are so few things you can do exactly. And you'd certainly like to be able to get the partition function of the easing model for non-planar, for Z3 or something like that, or with an applied field. So the goalposts now shift, and we look for a randomized approximation scheme. So what's this? So imagine we've got a graph problem. So n of g is the number of structures, whatever they are, trees or matchings, structures in G. This is the thing we're trying to get. So we're interested in a randomized approximation scheme, RAS, which is a randomized algorithm whose output, so by that I mean, it doesn't mean a program that can use a random number generator, assumed perfect, or you can flip a fair coin. Randomized algorithm whose output, Z, which is a random variable, because it's made these coin flips, satisfies and I should emphasize that the randomization is all within the algorithm. We're not assuming that the problem instances are in any way random. So the problem instance is a worst case. The randomization is within the algorithm, so it's totally under our control. Satisfies a probability that this output is within relative error. So let's say, so what did I say? N of g less than or equal to z less than or equal to 1 plus epsilon n of g. With probability at least 3/4, say, on input. So now the input is not just the graph G, but also an error bound epsilon. Not anything strictly between 1/2 and 1 will do here. Once you got above 1/2, you can start repeating the experiment and bootstrap yourself as close as you like. Right. So this is a number you're trying to let's be specific. Suppose G, you've got a graph G and you want the number of perfect matchings in it. Now I've moved the goalposts. I say you don't need to get that exactly. You just need to be within relative error epsilon. And it's a randomized algorithm, so it can go wrong, and it gets there with probability 3/4.
Sorry, Mark, doesn't epsilon have to scale with the
So we'll be coming back to that this afternoon. But this is just, I haven't said whether this is efficient or not. But again, what I'm shooting for, so I'll talk about complexity this afternoon. I'm shooting for an algorithm which is sort of polynomial in the size of the graph, certainly not exponential, where I don't have to pay too much. Obviously, as epsilon gets smaller, running time is going to increase, but I want it to scale nicely, say as a polynomial in 1 upon epsilon. Okay, but I just want to leave efficiency as a loose concept at the moment. And again, there's only one golf club for this stuff. So let's have monomer dimer as an example. And, this is going to be very impressionistic. So that's our problem that we want to solve is instance is a graph G and an error epsilon greater than 0, output the number of matchings. So what I had before were perfect matchings, right? So they had to cover all of the vertices. You had to pack those dimers in perfectly. But now I'm just saying you've got a bunch of edges, and they don't have to cover everything. The only constraint is they're not allowed to overlap. So there's no pair of edges in the matching which have a vertex in common. So scared to mention physics now, but so this is monomer dimer, so that the edges which are in the matching are the dimers, and the holes which are left are the monomers.
What?
Monomer. Okay, now this, as we'll see this afternoon, maybe, well, what I could say at this point, without bringing in any complexity, is that no one has an exact algorithm for this, unlike even for planar graphs, right? Even if I restrict to the situation where I have an exact solution for perfect matchings, there is no known efficient algorithm for this. So every algorithm for solving this problem scales exponentially in the size of the graph. Right, so how do we go about this? We use Markov chain Monte Carlo. And these are very simple algorithms, but the analysis can be quite tricky. And an algorithm which is efficient in theory may not count as that efficient in practice. So what you do is you, going back to our example, we set up a Markov chain whose state space is all the things of interest. So let's have one thing of interest here. See, I haven't covered, that's a typical matching or a monomer dimer cover, and that's a monomer there. So we set up a Markov chain on state space omega, which is just all matches. G. And we just have to invent so that, well, actually, I want to set up the transition probabilities in such a way that it's ergodic and the stationary distribution of the Markov chain is uniform. But actually, I need a little bit more flexibility. So what I'll have, the reason we need the flexibility, we'll see in a moment. So it's this, which has a stationary distribution pi satisfying pi of a matching will be proportional to lambda, some real number, positive real number, to the power n. So I just want some mechanism. I just need some mechanism for being able to control the size of matching. So if lambda is 1, then this is the uniform distribution of matching. If lambda is bigger than 1, then I'm favoring the bigger matchings. So by controlling lambda, so this Markov chain will be depending on lambda, and it'll have a stationary distribution, this, and that's the easy bit of it. It's very easy to construct these things. So in this case, and so this kind of approach goes back, I should get Broder's name in here. We're suggesting this kind of approach. And of course, the physicists were doing this before that. So this was probably the first time that a rigorous analysis was attempted, at least. You can, in this case, what you can have is, well, addition and subtraction of edges is enough in itself, but actually, in the classical analysis, it turns out to be easier also to have a sort of displace move as well. So it's traditional to have add, subtract, and displace. So you can imagine that, so here, I'll give an experiment that describes to you implicitly the transition probabilities. You choose an edge uniformly at random from the graph. And if it happens to be, so I maybe choose that one. If it happens that the edge, both endpoints are free, then I'll add that edge. This is the version with lambda equals 1. Okay. If I happen to choose an edge which is present in the matching, then I'll subtract that edge. And if I choose an edge which is blocked at one endpoint and free at the other endpoint, then I'll add it and subtract the other one. So those are the. You don't really need that last one, but it kind of improves the analysis. It improves the analysis at least, and probably improves the running time, I guess, as well. So you've got those moves, and if you did those all with, just like I said, without applying any filter to it, that will give you the uniform distribution because it's symmetric. So if every one of those moves I made has a symmetric make, adding and subtracting and displace is symmetric. Right. So this is a symmetric Markov chain with constant transition probabilities. So it's ergodic. You could rip off all the edges and put them back in again. So its stationary distribution is uniform. And to get the lambda, all you do is you put a bias in favor of adding as opposed to subtracting. Yeah.
Displace, how do you...
Oh, displace is, I choose an edge uniformly at random. It happens to be an edge which has a monomer at one end and a dimer at the other. It's free, has one free endpoint, it has one blocked endpoint. And I add the edge, and I subtract the edge which caused the block.
And if you have to pick an edge that's blocked,
Oh, if you pick an edge, that's the first one. If it's blocked in both, then you do nothing. You stay put. Yeah.
So it's involuntary.
Hmm?
So this is involuntary. This process is involuntary. Come back to where you begin with. If you happen to do this to the same edge you...
Yeah, that's right, yeah. Well, not quite. No, not the way I've not quite. You could make it into that, but the way I described it, it's not, because if I selected that edge, I would include it and exclude that. But then if I selected that edge again, I would have to take it out. So to get that effect, it's not quite, no. You could make it. You could couple it. You could couple it so that it was like that. Okay, so what's the good of that? So, well, firstly, it's no good if the rate of convergence to equilibrium of that Markov chain is exponential. So that can easily happen. That although that is the stationary distribution, it might take exponentially many steps to get close to that distribution. So, and this is the main sticking point, and this is where the mathematics comes in, but we're not going to have any of that. So we have to come back on March the 20-something for that stuff. So that's one point. And it turns out that in this instance, the mixing time, the number of steps that you need to take before you're close to equilibrium, turns out to be small. Just to point out that that's a non-trivial issue, if I went to independent sets, if I went to the hardcore gas model, that would no longer be true. So if my states were independent sets in this graph, and I did a simple insert-delete Markov chain on that, then certainly there'll be circumstances in which convergence to equilibrium could be exponentially slow. So it's a definite feature of the model. So it's a very special feature of matchings that this works. Okay, so that's one point. So I'm going to have to exclude that all. So that's a lot of nice stuff. But at least I guess I have to explain why it might be a good idea to be able to sample those configurations. Beyond the fact that you may actually be interested in what random configurations look like. So that's a possibility. Okay, but suppose now you want to evaluate the partition function. So you want to evaluate this thing. You want to evaluate the normalizing factor that makes that thing. What's the constant proportionality up there? It's this It's this partition function. We want to evaluate that. How do you do that given these samples? So you can do it just using it as a black box. So we have this Markov chain running in the background, producing samples from a distribution which is quite close to this one. So with all matchings of a certain size being equally likely. And then by varying lambda, we make the larger matchings more or less likely. So how are we going to use that in order to evaluate this thing? Well, this is going to get very hand-wavy, but a crucial fact about matchings is that they're log concave. So if nk is the number of matchings of size k, then this sequence is log concave. So if I look at the logarithms of those numbers, it's a concave function. And that means, so in this very hand-wavy sort of impressionistic presentation, it means that if you plot the number of number of matchings of size k as a function of k, you'll get something that looks a little bit like normal, right? So there's only one matching of size 1, and then it will grow up to a peak somewhere, and then it will go down. And well, of course, it won't necessarily go down to. There'll be some perfect matchings in general. So you get a diagram that looks like that. So this is all very impressionistic now. Now, when lambda is very small, if lambda equals 0, this is pretty easy to compute because you just get one term, so it's just 1. Only the empty matching. So for a very small value of lambda, you can certainly do this, but you're interested in some bigger value of lambda. And how do you get? So what you do is you start with a small value of lambda where you can get hold of this thing and gradually increase it, and you do it in steps. And you so you're stepping up the lambda in discrete steps, but not too much, and trying to evaluate how much z changes. So trying to get at this ratio. So I start with say I know I've got an approximation to this value. I want to now bootstrap up to this larger value of lambda, which I can do if I can figure out that ratio. And it's possible to figure out this ratio because of this sort of structure here. Because for any particular lambda, so adding the lambda factor is not going to affect log concavity. So you've always got this picture. What happens as lambda increases is that you push the hump up to the right a bit. So this gradually sort of goes up until you get to the point that you're interested in. And the point, then using standard Monte Carlo ideas, you can use the samples to compare the areas under those curves in effect. Okay, I mean that's pretty much all, since I'm already overrunning apparently, I want to say there. But somehow this log concavity is crucial in two ways in this. So somehow there are two sticking points where things can go wrong, and they're both cured by this. One is in the mixing. If we had something sort of bimodal, some kind of combinatorial structures which had this bimodal distribution, then we're going to be in trouble, because it's likely that the Markov chain will spend a lot of time here, stuck in this metastable state, and it won't explore stuff over here, because it's got to get through this constriction. So that's one reason that the log concavity is good here. And the second is, even if we could fix that problem, somehow to get this argument going, to be able to say that we can evaluate the partition function by gradually varying lambda, That's going to go wrong because what will happen, instead of this nice smooth picture, is that at some point the hump 1 will dominate, and then very quickly, as we make very small change in lambda, suddenly the other hump, this one will disappear and the other hump will dominate. And so we won't be able to make the jump between the two. So somehow this smoothness is critical at 2 points in the argument. So I should say that this, so the original, what I'm describing here, and I've missed out all the interesting stuff, obviously, for the monomer dimer. This, so that was joint work with Alistair Sinclair, and then more recently, either 2000, we got a polynomial time, sort of an efficient one of these approximation schemes for perfect matchings, but only for bipartite graphs. So it's still open for general graphs. So that was with Vigoda. So yeah, but I think all of that. Well, no, the earlier result about the monomer dimer systems, that's in the ETH notes, but those notes predate the later stuff there. So the capsule summary, I guess, is that in the circumstances where we know how to count things exactly, it's almost invariably because we can reduce to the determinant, which can be evaluated by Gaussian elimination. And if we can't do that, the next best thing we can do is to get an answer which is within small relative error, this randomized approximation scheme. And efficient ones of those, when they exist, almost inevitably exist because there's a rapidly mixing Markov chain that can be exploited to give samples, which can be exploited to do the counting. And aside from the things I've described, monomer dimer in bipartite, there is also ferromagnetic easing model in arbitrary graphs, and even with an applied field, provided that applied field is consistent at all atoms. Linear extensions of a partial order. Well, that's enough. That's enough for the time being. So, then this afternoon, what I'll come back to is kind of the opposite end of the scale. Those problems that we appear not to be able to solve, those problems where we appear not to have efficient algorithms, can we explain that phenomenon some way? Okay, so that's it for now. Yeah.
Towards the end, you were approximating the value of z at 1, right? That was the
I'm-
of all this analysis, or you were trying to get all of the sequence?
So I think the typical game is that
No,
you.
the process that you described right there. So the point of that was to approximate the value of z at 1, or was it something else?
Well, I mean, I can do it at any value as long as lambda isn't too big. So what happens
Yeah, but can't you just sample directly then?
when lambda equals 1? No, the only known way of sampling, the only known way of sampling matchings at random is by Markov chain simulation. There's no direct, yeah.
But well, this elaborate process tells you the value of z at some lambda, right?
Mm-hmm.
Given the value of z at a different.
Yeah, you have to start small where you
at a
know what's
smaller
going
value.
on.
So why do you have to go through this? It was maybe I missed.
Oh, the reason you can't make big jumps. Yeah, if you make small jumps, it takes you too long to get there. If you make big jumps, these humps have got too far apart, and I didn't say what my estimator was, but its variance will get huge. So I need to. So the mixing will happen at, but I'm at my estimator will be some ratio, and that ratio could go bad if I allow the humps to get too far apart. So it's just keeping the variance down. And there's a trade-off, and I should say very little work has gone on to theoretical work has gone into exactly how to do this process in the most efficient way. But recently, I should give these guys a plug. And it's a new guy. So it's some old guy. It's some old Stefankovic, yeah. Van Parler and Vigoda. They look at this process, And they have an adaptive scheme where they take small steps where they need to, and then they can make giant, much bigger steps than you would imagine at other points. And they've basically got an optimal way of choosing these values, and provably optimal for over some quite large class of processes. So that's quite interesting stuff, which I should have got into the talk. That was last year.
I've got one comment and one question. So which one do you want first?
So it depends whether the comment is positive or negative.
The comment is very positive. Well, okay, so the comment is, so suppose you take your monomer dimer model, and so you give a certain weight, a Boltzmann weight for monomers. Okay, so if that weight is non-zero, then the model is no longer conformally invariant. However, suppose now that you throw into the game another weight, say you are on a square lattice, and you give a special weight for lattice faces where you have on each side of the face a couple of aligned dimers, right? Like this or like this. So then if you choose that second weight as a special function of the monomer weight, then you get back conformal invariance.
Right.
So
Now,
that-
whether you would have mixing at that is unclear. Obviously, if that coupling you're suggesting was too strong, you'd be sunk, because presumably there'd be a phase transition
Right.
where there would the dimers would tend to be horizontal or vertical. But presumably that's not conformally invariant. So you're operating in a zone which is
Exactly.
and therefore it's going to be quite. I wouldn't like to say how that's like you for Z2, say.
Yes. So okay, that was.
So there's a very specific coupling that you introduce, which I don't know.
No, but that was
It might
that was
be-
the comment. So here comes the question:
Yeah, okay.
What is the dynamical exponent of this add, subtract, displace algorithm?
The dynamical exponent. So at some point, my physics runs out.
Okay,
So
let me rephrase it.
what's the spectral
so
gap or
the best thing you can. Okay, so suppose you have one configuration of your dimer monomer problem, and you want to get to some other configuration which is totally independent. So you introduce some kind of overlap to measure whether it has become something completely different. So the best thing you can hope with your algorithm is that if you have n edges in your graph, that you will become completely independent after the order of n moves of your algorithm.
yeah.
But it might be that it is not n, but n to some power.
Right. Okay. So
that
it's
power
not known.
one, or
It
is
does
it-
not know where it is. So so the current arguments, which I didn't talk about at all, would give you n times m. So m is the number of edges. So if you're thinking, if you want to restrict to planar,
Right. Well,
or to graphs of constant degree, think of m equals n. So it's n squared with some log terms and stuff. So I would be interested on, where is it in the range? I would say n log n. So the kind of computer science view counts that optimal case as being n log n. Because there's a difference between sometimes the dictionary is not exact. So optimal mixing in computer science tends to be n log n because of the coupon collector. You have to hit all the sites at least once in order to be kind of mixed up. And the physicists tend to think of spectral gaps, so they either think of n or even constant if they're thinking about exponential 1 updates at sites. But there is a gap, and I have no idea whether there are.
For log n, you're telling me that it is
So
optimal, right?
So we have an upper bound. We have an upper bound on the mixing time of this chain, this relaxation time, or whatever you want to call it. But it does not meet the obvious lower bound, and so there's quite a big gap. And it'd be interesting to know for this problem what the truth is actually.
Are you free for lunch?
That's a good
I guess I'm gonna have to have some lunch. Yeah.
Okay, let's leave it at that. Thank you, Devin.